I start the recording. So hello, everyone. Welcome to our seminar. Today, we are extremely happy to have Professor Antonio Riotto from the University of Geneva, and he will tell us about primordial black holes in the era of gravitational wave astronomy. So please go ahead.
Okay, thanks a lot for the invitation. It is really a pleasure to give a seminar. Again, I apologize for the unusual time and to not be there in person. So the topic, as Andrei said, is primordial black holes and gravitational waves. So both of them, both subjects are, of course, key prediction of general relativity. And today, what I will try to do is to tell you what we can learn about primordial black holes in particular through the gravitational wave. So that is basically the subject of my talk. So as you know very well, I mean, there have been measurements of merging of black holes. We measure the gravitational waveforms, whose strain is about 10 to minus 20, 10 to minus 21. So it's extremely weak, tiny signal, but it can be measured and has been measured by the LIGO and Virgo collaboration, as you know very well. So I'm not gonna spend so much time on this. I guess most of you are experts about this. So this is a curve, for instance, a set of curves for the current and future sensitivities of the experiments of current and future ones. On the horizontal axis, you see the frequency in units of hertz, and on the vertical axis, you see the characteristic strains, which goes like 1 over the square root of hertz. And in particular, I would like you to draw your attention on two lines, the green one, which is the Einstein telescope, which hopefully will be, since I'm on the European side, I will be advertising this telescope that will come into place in, we hope, in 15 years or so, which is next step compared to the LIGO and Virgo experiments. It's an underground one. And also the yellow line, which is the LISA experiments, a space-based telescope. And the reason why I'm mentioning them is, of course, because they are kind of complementary in frequency. The LISA as a deep in the peak in the sensitivity, which is about the millihertz, while the Einstein telescope goes up to 10 to the 2 hertz or the kilohertz. So this is also a familiar plot. I am sure you have seen it many ways, many times. This is not the most updated one. And the reason why I decided to show it is because in the next few transparency, I will be talking about the analysis that we have done in Geneva about the GWTC2, which is not the most recent release of data. From the quantitative point of view, nothing will change compared to what I'm going to tell you with the GW2 with respect to the GW3. So here you have basically masses of the black holes that have been merged in units as a function of it's a catalog of all the events as a function of the mass. So you can see that basically the experiment have been detecting all kinds of masses so far, up to about 100 or so. So which makes the statistics already interesting to make a prediction in terms of primordial black holes. So black holes, very quickly, because I'm sure also you are expert more than I am in this subject. So astrophysical black holes are black holes that suffer of a lower limit, which is about a solar mass, which is called the Chandrasekhar limit, coming from the fact that this object have to form. And so there is a balance between gravitational force and the pressure. On the other contrary, the primordial black holes, they do not suffer from such a strong lower limit. They can go down to very low masses. In particular, in fact, there is no lower limit. But for the sake of today's talk, I will concentrate on masses which are larger than 10 to minus 18 solar masses, because I want to consider primordial black holes that do exist today, even though they were formed in the universe, meaning that they have not time to evaporate according to the prediction of the Hawking radiation. So 10 to the minus 18, roughly speaking, corresponds to an evaporation time which is corresponding to the current lifetime of the universe. So the key questions that people ask, at least the one that I think are interesting enough to be addressed, are the following. Do we know something about primordial black holes in terms of the current and eventually future gravitational signals? What can we learn about them? Second question is, what are the smoking gun of primordial black holes? Meaning that when we see a merger of black holes, what can we say about the nature of the black holes? Are they astrophysical or are they primordial? Maybe the most interesting question for some people, including myself, is the following: can the primordial black holes account for the full amount of the dark matter? If the answer is yes, this is extremely important, because primordial black holes can be objects that do not invoke exotic physics beyond. Of course, there will be some assumption, and I will make it clear in the following. For instance, we hypothesize a period of inflation, but apart from that, we do not, in that case, will not be constrained of invoking some WIMPs or axions or whatever beyond the standard model physics. So the primordial black holes are as I said, they span a large interval of masses. Here is a plot where on the horizontal axis you have the mass of the primordial black hole either in units of solar masses or grams, and on the vertical axis we have this parameter FEBH. That is the ratio of the amount of energy density omega of primordial black holes compared to the dark matter. So when the number is 1, the full dark matter is comprised of primordial black holes. Otherwise, if you go to 10 to minus 2, for instance, only 1%. And here I highlighted these curves are the present constraints that you have. For instance, when you go to the range interesting for LIGO and Virgo, around 10 solar masses or so, you have constraints that come from the microlensing, or for the CMB on the right part of the diagram, where basically you account for the fact that black holes can accrete and therefore create a distortion of the CMB. What I would like to draw your attention on, though, on the other side, is this region, which I depicted in green, this kind of highway, which is going from 10 to minus 17 up to 10 to minus 12 solar masses, where basically there are no constraints, or better to say, there were constraints that because of the interest in primordial black holes, people have reanalyzed, and they discovered many ways out, many loopholes in the previous constraints, and basically the outcome is that in this region FEBH can be of order unity, which is extremely important because, of course, those primordial black holes that have a mass of around an asteroid, the typical asteroid, they can be the dark matter. So I will come back to this issue in the following. So
could I ask a question on this? Because this plot, sorry, I have some background noise. I've seen various versions of this, so I guess I have two questions. From 10 to the 10 to the minus 12 to 10 to the 3, I've seen versions where the constraints are significantly lower. And then can you just say how sure are we that the asteroid band is really allowed?
Yes.
Yeah, just briefly.
So there were two strong bounds. One was coming from the femtolensing, and the other one was coming from the neutron stars. So the idea was basically people. So the different bounds were criticized on different grounds. The first one was the fact that in fact the femtolensing bounds that were constraining that range as well was ruled out by the fact that people realized that there were wave effects that were not taken into account, and therefore the limits were much bigger than thought. So there is a very nice paper by people at CERN that I can give you later on if you're interested, which is about now 4 or 5 years old, where the people, they have realized, and even the collaborations that put the constraints, they have now accepted this point of view. The other bound was coming from neutron stars, meaning that, of course, the fact of having a large density of primordial black holes was giving the possibility that the neutron star the primordial black holes were captured by a neutron star, and of course this neutron star was being eaten by the primordial black hole with a given amount of time. But even there, the limits were based on the fact that the amount of primordial black holes in globular cluster were really kind of unrealistic. I mean, a factor 10 to the 3, 10 to the 4 more, I mean, larger than a reasonable number. So people also reanalyzed that and concluded that the constraints were too strong. So those are the ones that I believe have been scrutinized and eliminated. I can give you a reference where it's not really a review, but it's a more a technical paper where this is discussed in details if you're interested.
Super, thanks.
Okay. So now the other question that I would like to ask even briefly is that where the primordial black holes may come from. Of course, they are creating the early universe. There are many scenarios where the primordial black holes are created. Maybe the most standard one, the one that I would like just to put your attention on, is the fact that if you have a large overdensity in the early universe generated by whatever mechanism you want, if this overdensity is larger than some critical number, which here are indicated by delta C, which is of order unity, this overdensity will be collapsing into a primordial black hole. This happens even during the radiation phase, even though there is a lot of pressure. So the overdensity have to be large enough to overcome the pressure of radiation, and they may form, in fact, a primordial black hole. So the idea is very simple. Suppose that you have generated such overdensity on a given wavelength, maybe coming from inflation. Then when the universe is expanding, at some point this overdensity will re-enter the horizon. And as I said, if the overdensity is large enough, a black hole will be forming. Now, it's very intuitive to understand that the mass of the primordial black hole will be related to the mass inside the horizon at the time in which this collapse is taking place. So the mass of the primordial black hole will be really the mass of the horizon at that time. Of course, as you can understand also very intuitively, it's a rare event because you need large overdensities, almost of order unity, let's say a factor of 0.1 or so. And the question is, where do they come from? Well, people have proposed this standard mechanism that comes from inflation. Okay, I'm not going to spend so much time on inflation. You know, the inflation is a period driven by, most probably by a scalar field, which goes the name of the inflaton, where the scalar field is such that the potential is very flat. So the universe is dominated by the vacuum energy. Because of that, the Einstein equation tells you the scale factor is growing exponentially. And you can create perturbations by quantum mechanics, basically. And the curvature perturbation, which is the gauge invariant quantity that you want to look at, think of it as a kind of gravitational potential. The power spectrum goes like 1 over phi dot, where phi dot is the velocity of the inflaton field. So if during inflation you have a period where the inflaton field is basically spanning a region where the potential is extremely flat, so phi dot is extremely small, you have a jump in the power spectrum, a jump compared to the CMB scales, which are very large, and where the power spectrum is of order of 10 to minus 10 or so, 10 to minus 9. But at much smaller scale, you have a jump in the power spectrum, and if you go up to values of order 0.1, at small scales, you can create such large perturbation. And this region of the parameter space of the momenta or wavelengths where you look at on the right-hand side of this diagram, there are basically no constraints. So you can have large fluctuations at very small scales. So the idea is very simple. So you have the curvature perturbation as a function of the momenta. So here on the left, you have the CMB part, which is a level of 10 to minus 5, 10 to minus 4. And then on the right-hand side, at very large scale or small scales, you have a perturbation which grows up to 10 to minus 1 or so, in order to eventually give rise to primordial black holes when the fluctuation on those scales re-enter the horizon much after inflation. So if that happens, what are the primordial black holes properties at the beginning when they are formed? This is important because, of course, if you want to now to understand what is the phenomenology of the primordial black holes merger, we have to understand the evolution from the moment they are born up to the moment they are merged. Okay, so first of all, the primordial black holes, when they are formed, in this kind of scenario at least, they are not clustered. It's very intuitive to understand why, because as I said, the primordial black holes, first of all, they are very rare events. So it's typically only one horizon up to the 10 to the 10 or 10 to the 20, it ends up in a black hole. So they are very rare events. And second of all, they are separated by horizons. So in that sense, there is no way they can be correlated unless you have some non-Gaussianity, but this is not the scenario that I'm imagining right now. Also, they are discrete tracers, so they are, they are born like they have a kind of two-point correlator, which is basically Poisson-like. So this is the first kind of property that I would like to highlight. The second one is, are they spinning or not when they are born? Well, the answer is no, because as I said, again, they are rare events, and they correspond to you have a distribution in space of this kind of field, and only the maxima, the peaks of this field, because they have large overdensity there, they can collapse and give rise to a primordial black hole. Now, if you're familiar with peak theory, there is standard paper in cosmology written by which is really named BBKS. BBKS tell you, in fact, that when you look at large peaks, so large overdensity in space, they tend to be very, very spherical. So the sphericity is really a property of these large fluctuations. Meaning that when this collapse is taking place, then of course you have small tidal forces because of sphericity. You acquire a small spin, but it is over the order of 10 to minus 2 in units of the spin divided by the mass of the primordial black hole square. Of course, you have some spin because the surrounding structure of the universe is not perfectly uniform. But the spin is basically zero. So in first approximation, we can assume that these primordial black holes are born unclustered or Poisson-like clustered and spinless. The other property that I would like to draw your attention on, but in fact is more a kind of phenomenological statement that I'm making, because this is model dependent, is what are the distribution in terms of masses? What is the mass function? Well, in general, people, and what I will do also in the following, they assume that the distribution of the primordial black holes, of course, this is not completely, proposed on the table like this. It's just by hand. This comes from some computation in some models. It is a log normal distribution. So basically, you have a quantity MC, which tells you where the peak of the mass function is, and a given variance. When the variance is very small, this function is very peaked. When the variance is very large, you can think of distribution in terms of mass as a kind of uniform distribution. So you can change sigma and MC according to the model prediction that you like most. So this is what I would like to consider in the following as well. Okay, so first of all, let me try to ask the first question. What is the state of the art in terms of what we know about primordial black holes, and what is the current data about gravitational wave telling us about primordial black hole? So as I told you at the beginning, I will present you only an analysis for the GWTC2, which contains about 50 mergers of black holes. Most of the events are consistent with the fact that they are mergers of approximately equal mass black holes. And also notice that, if you look at this picture where you have different observables, that I will go back to this later on, you don't have to focus on now on each of them. But the most important information is that in this catalog and also in the new one, an abundant margin of data have black holes with large spins. Okay, so you might think this is contrary to what I told you, because I told you that the spins are born with zero spin, basically. But as I will show in the following, even primordial black holes, they tend to acquire large spins during the evolution, during the period when you go from the moment they are born up to the moment they are merging. So what are the...
Is there a meaning to the color coding from top to bottom? Chi is a spin there, but the color code?
Yeah, chi effective, the spin that I'm going to define later on. No, the color code is basically, to me, it is just, it is just to distinguish the data. I don't remember any particular meaning to that, but I might be wrong about that.
Cool. Thanks.
So I don't remember that in the paper that describe the color to be meaningful, I would say. So the quantity that I would like to draw your attention on are the quantities that are best measured by the experiment. So which is this calligraphic M, which is a combination of the masses of the two objects that are merging. The Q, which is the ratio, which goes from 0 to 1. And then also the chi effective, which is a kind of weighted combination of the two spins of the object which are merging, projected over the total angular momentum. So those are the three quantities that are best measured right now. There are other quantities which are not very well measured, so we drop them. For instance, another combination of spins, but we restrict ourselves to this three kind of data because three kind of observable, because they are the best ones which are measured. So let me now spend a little bit of time to tell you what is going to happen to a primordial black hole from the moment it's born up to the moment is encountering another primordial black hole or another black hole and is merging. So as I said, they are born in the radiation phase very early in the universe, about 10 to the 10 in redshift. Then, of course, time to time, they have a given possibility, a given probability to encounter another primordial black hole. That depends on the way they are distributed initially. That's the reason why I was stressing the fact that initially they are Poisson distributed. And then they decouple from the Hubble flow and then they start, of course, a kind of orbiting dynamics, one around the other. And this is basically even taking place before the epoch of matter radiation equality, when the redshift was about 1000. Then, of course, there is a period where they start accreting the surrounding plasma, and eventually they merge to give a signal. So let me go through even briefly through these epochs. So the first point to highlight, I believe, is the fact that if FEBH is more than 1, meaning that the primordial black holes do not form the totality of dark matter, they will start accreting also the other components of the dark matter that exist, like, for instance, WIMPs, weakly interacting massive particle in supersymmetry, for instance. And you can easily compute the halo that will be forming around the primordial black hole, and end up with a result which tells you that, in fact, at 0 redshift or very small redshift, this halo will be even, 1,000 larger than the mass of the primordial black hole that has been accreting up to that time. Of course, this is a kind of back on the envelope estimate, in the sense that people have done it in the last few years using this Bondi oil accretion model, which is very simplified. But when they go into more details about the possibility that the accretion is not exactly spherical and so on, the numbers does not change dramatically. Also, another important point is the following: that, of course, when the binaries form, accretion will also take place onto the binary, and you can compute what is the dynamics of the masses of the two primordial black holes. And it's not difficult to realize that, in fact, that the masses, even though they are born different, at least for the primordial black holes, they tend to be equal, because they start transferring masses from one to each other till the fixed point is reached. So one prediction of the primordial black hole scenario is the fact that if they are born with masses which are larger than about 10 solar masses, this is kind of in a ballpark scenario, 10 solar masses is a number that to remember. They can accrete sufficiently in order to reach the point Q = 1, where the masses are basically equal. Meaning that if I look at the 10 to minus 12 solar masses, this is not going to happen. Okay, but in any case, the merger of a 10 minus 12 solar mass is not going to be observed, so this is not an interesting for us. We only want to look at the data. So and the accretion will be taking place not up to the end. It will take place up to a moment that we define to be Zikatov. Zikatov is a parameter that we propose in our papers in order to mimic somehow or to replace or to introduce some ignorance about the full dynamics of the accretion. So in simple words, Zikatov is the redshift at which accretion will stop. Accretion can has to stop or will stop because of many things. For instance, at some point you start forming large-scale structure. I mean, the delta rho over rho around the primordial black hole will come over the unity, and therefore the masses, if you remember the formula, I was telling you that there is this kind of dependence on the inverse of the cube of the velocity of a kind of effective velocity, which takes into account both the relative velocity of the primordial black hole with the surrounding plasma, VREL, which is here indicated by this quantity VREL, and the sound speed. So what happens is, in fact, this object will drop to zero very quickly when, for instance, the structure will start form and the surrounding plasma gets heated, and therefore at some point accretion will stop. But since this depends very much on nonlinear physics and on the details of the dynamics, nobody knows how to control or to predict the Zikatov. So for the time being, what we decided to do was to use it as a free parameter. Okay, so this is very important. We are now hiding our ignorance about this nonlinear dynamics in this parameter Zikatov. Another important point is that what happens to the mass function. As I said, because of accretion, the black hole will start accreting mass, and therefore the mass function will start having a larger tail at larger masses. Here, for instance, you see how the mass function will change according to the Zikatov. If Zikatov is very small, you have more time to accrete. So of course the orange line will be on the top. While if you increase Zikatov, so you give less time to primordial black holes to accrete, the mass function will basically grow a little bit less. Another important point is what happens to the spin. As I told you, even in that case, the spin is increasing for primordial black holes. Why? Because you have accretion. Again, if there is an angular momentum of the matter surrounding the primordial black hole, this angular momentum will be transferred to the black hole, and you can easily you can study the dynamics in the case of a perfect disk. Of course, again, the dynamics are a little bit more complicated, but the output of this kind of study is the fact that the spin of the primordial black hole, even though it starts from zero, you will start accreting and acquiring a spin. And here is the dynamics, of course, this chi parameter that is before as a function of redshift. You have to go from right to the left when you go from early epochs to more recent epochs. And you see that there is a tendency of the primordial black holes to acquire a very large spin. Of course, I mean, if you give them an infinite amount of time, they will go to 1. 1 is the extremal case, it's the upper bound, but in general, the lesson to take home is the fact that there is a kind of correlation between the mass of the final mass of the primordial black holes and the spin, meaning that if accretion is very efficient, the primordial black holes will tend to acquire large masses and also acquire at the same time large spins, and vice versa. Meaning that if one day we will have a way to detect a merger event out of which we can say that this comes from primordial epochs, and we see that the mass is large but the spin is small, this will be in contrast to this kind of prediction. So it means that either a prediction is wrong or the event is not really a primordial black hole. Then, of course, we have to compute the measure rate. This is not. This is kind of a standard result. You start from a Poisson distribution. You let the primordial black hole evolves. You compute what is the probability to form a binary system, and then you compute the measure rate. The measure rate per unit volume per unit time. And then I would like to address your attention on two behaviors. First of all, the kind of universal behavior as a function of time, which is this factor here in units of T0, which is the age of the universe, and also the power of the FBH, which of course goes to 0 when FBH goes to 0, which is kind of trivial. But the function of time, which is kind of, okay, I mean, there is nothing profound in these numbers. They come out of a computation. But I would like to draw your attention on this because I will talk to you about later on about future experiments and how to distinguish between astrophysical and primordial black hole signals. the time dependence will be one of the key quantities that I will invoke. So if you can remember this dependence, I will of course give you I will go back to this issue later on, but this is important for the following. Okay, so now once we have a kind of handle on the evolution of the primordial black holes from the moment they are born up to the time of merger, the question is how can we what the data can tell us about the nature of the merger. Well, first of all, we have to understand how to compare the primordial black holes with other scenarios, the physical scenarios. So here I'm not an expert, of course. I have not, I never worked so much on the astrophysical populations, but what I learned, you know, in the last few years is the fact that there are basically two broad classes of formation of black holes in the literature from astrophysics. So one is called the isolated formation, where basically the binary forms mainly in galactic fields, and through a process that goes under the name of stable mass transfer or common envelope, which is SMT or C in the community. So what happens is that you form a black hole, and then by mass transfer, you basically start accreting, you form another black hole, and then eventually you have a merger. The other big class is called the dynamical formation, where you form the binary forms in globular clusters, or as people say, nuclear star clusters, and the binaries form by encounters and with the release of gravitational waves. So those are the two broad classes. They have prediction in terms of the spin, in terms of the other variables that will be analyzed. But what we have done is basically a Bayesian evidence study of the, as I said before, of the GWTC2 data. So we have a set of event parameters, which are the masses of the black holes, the chi effective and the redshift at which the merger is taking place. And then we have a population hyperparameter. So for the primordial black holes, it will be the MC, which is, if you remember, the peak of the mass function, the sigma, which is the width. You have the FBH and the cutoff at which the accretion will stop. For the other parameter, for the other astrophysical models, you have basically either the spin chi b, alpha, which is the efficiency of the CE formation method, and also the n parameters, which tells you how to distribute the number of events according to the classes that we have, which is completely free. We treated them as free parameters. So at the end of the day, I mean, I don't want to spend so much time on this, it's kind of technical, but what we computed was the posterior distribution. And then what we did was a kind of Bayesian evidence analysis, and we compare basically different kind of class of models with the PBH. Now, going into the main important point is the following. So what we came out was the following, that independently of the constraints that there are in the LIGO Virgo mass range for the black holes, the best values for the primordial black holes are the following. The FBH turns out to be very small, 10 to minus 3 or so, okay? And also the accretion is quite of moderate. Now, what is the meaning of this? The meaning is that basically in the LIGO Virgo mass range, the primordial black holes, they are not the dark matter. It's impossible to be the dark matter independent of the constraints. Notice also that these best values are in agreement with the constraints, so they do not violate the constraints, which is also quite important. But the message number one that I would like to deliver is that in the LIGO Virgo mass range, if there are primordial black holes in the events, they are not giving you the dark matter. So that's excluded. So that's the first message that I would like you to give. Okay. So having said that, maybe the other question that I would like to address is the following: what are the smoking guns? So how can I distinguish, of course, a primordial black hole from an astrophysical one? Because this kind of analysis that we have done was kind of blind. We never assigned to any particular event the label primordial black hole or not. So we just compare the class of models blindly. But once you have an event, when you look at a single event, how can you say something about the primordial black hole nature? Well, first of all, well, as I said before, kind of obvious. If you go to masses which are smaller than one solar masses, you can say, well, it's a primordial black hole because the astrophysical black hole, they suffer from the Chandrasekhar limit, which is the lower limit of about one solar mass. Now, some people criticize this point of view, and I also kind of agree with that, because there are other ways to have events with masses smaller than one solar mass. For instance, you can have Bose stars, for instance, and whose masses are precisely, they can be smaller than one solar mass. So, and they are not primordial black holes. So in that sense, you cannot say that if you see an event with masses more than one solar mass, that is necessarily a primordial black hole. So you can look at the spin, of course, of the primordial black hole, because as I said before, large spins are correlated with large masses. But this is not a way to identify an event, it's rather a way to exclude an event for the primordial black hole. So what I would like to draw your attention on the following of the seminar is about two things which are kind of interesting to me. One is the merger rate time evolution at high redshifts. That is, I think, is a very strong smoking gun from primordial black holes. And the other one is the stochastic gravitational wave background that comes from primordial black holes that merge at very high redshift. So I would like to discuss these two issues now in the rest of the time that is left. So let me go to the first one. So if you remember, I was trying to stress the point that the merger rate of primordial black holes, when you go as a function of time, they have this kind of universal behavior, which is basically the time to the powers minus 34 divided by 37. So here, what I've done, I plotted this merger rate, normalized to the merger rate today, as a function of the redshift. And you see here that the rate is increasing. This is a blue line for the primordial black holes, while for astrophysical black holes, it's dropping down. This is also very intuitive. Of course, when you go to very large redshift, you don't have structures, you don't have basically stars, so you don't have astrophysical black holes because those need stars as the first seeds to create black holes. Now we did an estimate of what is going to happen for future experiments, which I mentioned at the beginning of the talk, which is the Einstein telescope. So here on the bottom left of the slide, you see the sensitivity. Or better to say the horizon, the capability of the distance in terms of for different redshifts of the Einstein telescope. So you see here, for instance, a redshift of order of 30, which is quite large, in fact. The Einstein telescope will be able to detect basically the merger of black holes up to about 100 solar masses. So we did the following computation. We asked ourselves, suppose that in the future, what is the expected number of events that we expect from primordial black holes at very high redshift, where the astrophysical sources are basically wiped out. So you don't have any foregrounds from astrophysical sources. And then the number turns out to be 1,000 or so per year. If you say that the total number will be quite large, will be about 1 million of data, 1,000 is not an extremely small number. So we would expect that to be able to detect this number quite easily, and therefore that for me it's a very strong smoking gun, because not only will be able to measure the events, but also the time evolution of the events. And if the time evolution is the one that is predicted at least by the standard model, then I think this will be a believable smoking gun for the primordial black holes. Okay, so having said that, let me go to the other possibility, which is kind of related to the possibility that the dark matter is in fact formed completely by the primordial black holes. So the subject that I would like to address in the last 20 minutes or so, or 15 minutes or so, is the fact that primordial black holes do not only form gravitational waves through the merger of them, but also through the fact that when they are formed, the stochastic gravitational wave background is formed, and this is a kind of stochastic because, of course, it will come from all possible sources, from all possible directions from the early universe. So how does it happen? As I told you at the beginning, the standard scenario tells you that the primordial black holes, they form because of the collapse of large overdensities. Now, these large overdensities, unavoidably, they also source the gravitational waves. And this is the equation that I wrote down, even though in a schematic way. So the equation is for the Hij, the transient traceless part of the metric perturbations. They are sourced by derivatives of the gravitational potential that are there to generate the primordial black hole. So anytime you form a primordial black hole in the universe, you also form a stochastic gravitational wave background. This is really unavoidable. And so this is a second order source. As you see, it goes like to zeta, to gravitational potential. So it's clear that the 2-point correlator of this gravitational wave will go like the square of the power spectrum of the gravitational potential. And you can do an easy computation. It's not difficult to compute this correlator, to compute how much gravitational waves you expect. And you can say, well, suppose that I have a primordial black hole form at a given mass. This will give you the frequency of the gravitational wave, because you can intuitively think that the frequency of the gravitational wave will be the horizon scale at which you form the primordial black hole. And then you can compare it with the future experiments, like for instance the LIGO experiment. Okay. So omega gravitational wave, as I told you, will go like the square of the power spectrum. So you expect that this is at the level of 10 to minus 10 or so. And then of course, where is the peak of the power spectrum depends on where is the peak of your mass function of the primordial black hole. This is completely free parameter. We don't know where the peak is, of course, if there is any peak. But if you put a peak around the millihertz, then you enter in the sensitivity curve of the LIGO experiment. And this is very interesting because this is a very kind of nice coincidence. The coincidence is the following. The frequency of the gravitational wave that you form at that time when you form a primordial black hole is, as I said, of order of the horizon at that time. But the horizon at the time also fixes the mass of the primordial black holes, because I told you the mass is basically the mass inside the horizon, the volume of the horizon. So so there is a relation between the mass and the frequency of the gravitational waves. Now, if you plug numbers, there is a very beautiful coincidence which tells you that if you put the frequency to be the LIGO experiment, which is around the millihertz, you end up in a mass range of order 10 to minus 12 solar masses, which is precisely the range of masses where the primordial black holes can be forming the totality of dark matter. So this is a kind of nice coincidence, and it gives you a possibility to test this idea, to test if the primordial black holes form the dark matter, because the moment you say so, you have a very nice and well-defined prediction in terms of the gravitational waves, meaning that if the primordial black holes, they form the dark matter of the universe, the totality, the moment the LIGO experiment is switched on, they should see this stochastic gravitational wave background. If they don't see it, it means that this idea of dark matter in around 10 to minus 12 solar mass is ruled out. So we are waiting for these experiments with eagerness, because of course it's a kind of nice coincidence about this between the mass of the primordial black hole and the frequency that we can test. Now, having said that, let's go to real data. So the real data tell us that in fact there are a bunch of experiments that I'm sure you have heard of, these nanograv experiments that are measuring the possible imprint of gravitational waves on the millisecond pulsars, which apparently they have an evidence for some signal. And what I would like to do now is to elaborate about it, assuming that it comes from gravitational waves. So what these experiments they do, they measure nanohertz signals, and there is a prediction that tells you what is the cross correlation of the timing residuals from these millisecond pulsars, if the signal is coming from the passage of the gravitational wave stochastic background. So apparently what they have seen, the nanograv 12.5 year release of data, they have seen a strong evidence for a stochastic common process with about 45 pulsars at a nanohertz signal. So they have seen a kind of increase of the signal, kind of power law, which can be parameterized by an amplitude, which is about 10 to minus 5 squared 10 to minus 10, and a given slope, which is basically comparable. It's I mean, gamma equals 5. The 5 is just for historical reason, but the gamma, the power law to be 0, so gamma border of 5 is perfectly compatible with the data. So what we can do is the following. Of course, the collaboration never said that this is ascribable to a gravitational wave signal, but what you can do, you can play this game and say, suppose that the signal is realistic, and apparently, if you talk to members of a collaboration, it looks to be very solid. Of course, it's not guaranteed it comes from a gravitational wave source, but let's play this game. Of course, for those of you that are unfortunately old enough to remember when the COBE data for the CB anisotropy were released for the first time, the situation is very similar to what we had at that time in terms of gravitational waves. So at that time, the COBE they detected the monopole of the CMB anisotropy, but they didn't detect the higher multiples. We had to wait the boomerang experiment, WMAP, and now of course the Planck experiment to see the pattern of the CMB anisotropy with different multiples. Here the situation is the same. We might have seen the monopole, but we have to wait a little bit of time to see the real imprint of the gravitational waves into this millisecond pulsars data, and to check what is called the Ellings-Dons correlation pattern, which is really the footprint of the gravitational wave. The data now, as you can see, they're spread in such a way that you can distinguish between a monopole and the prediction, of course, of this HD correlation pattern. But the data in the future will become more accurate, and luckily and fortunately, we will be able to distinguish and to either confirm or to rule out the fact that these experiments for the first time have seen a stochastic gravitational wave background. We will see. Apparently, talking to the members of the experiment, they say that we don't have to wait a lifetime. We have to wait a handful number of years to have a clear pattern of what is going on. But for the time being, let me play the game, and let's suppose that this gravitational wave, this signal is coming from gravitational waves, and let's suppose that they come from primordial black holes. So what we have done some time ago was to say, let's construct a simple model of primordial black holes, and let's impose that this primordial black hole scenario comprise the totality of dark matter. So if you integrate this blue line, this mass function over the total mass range, you're getting 1. So this is what we are supposing that it does. It has a peak around 10 to minus 12 solar masses where there are no bounds. And then there is another peak at the QCD, because it is the fact that at the QCD phase transition, the equation of state is changing a little bit, and meaning that the threshold that is you have to form primordial black holes is lowering a little bit, and you have a peak because of that of probability. But of course, when you integrate over all range, this peak is not very important. So what we suppose is that, so the mass function here comes from, is not that we put it by hand, but it comes from a curvature perturbation, a gravitational potential perturbation that is flat in a given range of scales between k long and k short, so between 2 scales. This is we put by hand, so I have to admit it is not coming from a model. We just put it by hand. We say that is a kind of phenomenological approach. So once you have this kind of input, you can compute rather easily what is the amount of gravitational waves that you can see in nanograv. And of course, we set the amplitude of the primordial black hole curvature perturbation in such a way to have FEBH equal 1. And miraculously, what happens is that the nanograv data are perfectly fit. And also, which is quite nice, I believe, is the fact that this signal propagates up to much larger frequencies. So in other words, when an experiment like LISA will be switched on, we can check if this model is correct or not. In other words, we were looking for a cross correlation of data in order to have a way to test, or either to rule out or to confirm such a model. And apparently, the signal can be managed to propagate to larger frequencies in such a way that that we can test it in the near future. So this is a nice, I mean, of course, it's constructed by AND model. So it's an example of a model that Primordial Black Hole that works, but at least it is a testable one that you can rule out in the not a long future. Okay, so having said that, let me conclude, because as I said, I'm strict with time, but I would like to take some questions. So let me conclude very easily. So I've been trying to convince you that, of course, you know, we are entering, we are already in this era of gravitational wave astronomy, and I hope that I gave you one example, which is very hot topic nowadays, of primordial black holes, where you can say quantitative things about this scenario, of course, starting from some assumptions. And then you can either you can answer some questions with a given degree of accuracy, of course, which are interesting enough. For instance, whether or not the primordial black holes can be the totality of dark matter, which is, of course, a very interesting question, because, as I said before, if the answer is yes, then we won't be obliged to invoke physics beyond the standard model, besides inflation, for instance, but which is kind of already in cosmology a kind of paradigm, which has been accepted, I would say, by the large majority of cosmologists. And I think I will stop here, and I will use the rest of my time to take questions if you have any. And I would like to thank you for your attention. Thanks a lot.
Okay. Thank you so much for this very exciting talk. Yeah, so we have time for a few questions. Arkady, please.
Okay, so, thanks, Antonio, for the talk. I was listening another talk on primordial black holes from Sasha Dolgov, and my understanding is that he was with his collaborators kind of pioneers of this kind of primordial black holes. Yes. Right? In particular, no, as far as I remember, say they have this model of this mass distribution. I even remember that their characteristic, this MC, which you mentioned, was like 17.
Yes.
Compared with your 30. I mean,
yeah. So that number is not a prediction of the theory. It has to be.
Yeah. Right. I understand that it was a parameter they fit. Yeah, right. But still, you see, they have kind of particular. No, I mean, it was some parameters there to fit, right? But still, I wonder about your comments on comparison of the model, right? Because I mean, I guess the model's also different, not only the parameter, right?
No. In fact, you have to be, yes. Thanks for the question, because maybe I didn't stress that enough. Of course, what we have done, I think, more carefully, without taking anything to the others, is the fact that we included the full evolution of primordial black holes from the beginning to the end. So, for instance, the accretion and the impact on the spin, and including the spin, the analysis, the other groups in other recent comparisons, they have not done. So I cannot say, of course, I cannot be sure that the difference between 70 and 30 comes from there. But yeah. I would say, if you ask me, I mean, my first reaction would be, yes, it comes from there, because you see, there is a tendency of enlarging the mass when you go from 70 to 30, and this is because of accretion, I believe. So because, as I told you, the ballpark of masses where accretion is efficient is when the mass is larger than 10. So if you start with a mass of order of 17, accretion is unavoidable and will happen. So that will tend to increase the mass of the final black hole before the merger. Because of course, for us, the mass function is also changing with time. So it's not that the MC is an invariant quantity as a function of time. So I would say my answer is that, I mean, naively, I would think that the reason is because of that. But you are right to say that, of course, the number depends on the way you treat the data, first of all, and the way we have evolved the primordial black hole from the beginning to the end, I would say.
Yeah, but it means that more or less kind of physics is more or less similar. Besides that, you had this additional account for accretion, right? But also related to your talk, I wonder, in some there is this parameter which is I don't know of the order of tens of solar masses, but I believe your emphasis was on this kind of range of very small masses, right? What is the relation? Because I do not know.
So there are basically two things that you can do in this business. So either you look at the data coming from gravitational waves from the merger of black holes, meaning that you have to analyze the data in the LIGO Virgo mass range, about 10 solar masses or so. Then there is the other picture where you go to much smaller masses. There, of course, the merger is irrelevant because even though they merge, the gravitational waves frequency is not detectable. So you have to look at another kind of gravitational wave, which is the stochastic gravitational wave background. Okay, so those sources are completely different. So according to the mass range, you have to look at two different sources. And this is what I've been doing in the two parts of the seminars. And I'm sorry if I was not clear enough to distinguish them, but that is what the people do.
I see. So in this way, it's like I'm sorry, I'm kind of ignorant in this, so I could ask very stupid questions, but still, in this way, it means that by itself, this range of large masses in the model does not predict distribution for smaller masses, or you see. So you mean that you need independent, kind of comparison to.
No, it's not a stupid question, because of course, if you predict a mass function, you can correlate the two masses, of course.
Yeah.
But usually the mass function has the property that is peaked around one. I mean, either you have many peaks or you typically have only one peak. So, and the peak, where you put the peak is completely independent. It's a model dependent. Okay, it's your choice. So either you have many choices. Either you put a mass function, we have only one peak, and then you decide to pick either at the LIGO Virgo mass range or much smaller, or you invent a model, and that's up to you to say, well, I have several peaks, and then I correlate. But of course, that you do it by hand. So this is in this business. Unfortunately, the mass function is an object that it's completely theoretical dependent. So it's basically up to you what you put.
Yeah. So in this way, observation at these large masses does not fix for you what's going on at low masses. I see. No. I got. Okay. Thank you for. It was very, very clear stated. Thank you.
Okay. Thanks.
Okay, maybe one more very short question. Yohei. Okay. I think Yohei raised the hand first, so please. Yohei?
Yes, I hope you meant me. I couldn't hear you, Andrei. So just thank you very much, Antonio, for the very nice talk. I was wondering in your previous slide where you showed the omega in your model, what sets the high frequency cutoff, and, what in the model can you change, to move it around if possible?
Yeah. Okay, so what fixes the two cutoffs, the infrared and the ultraviolet, is precisely this K long and K short that I put. So what we did was to say, look, there is a kind of flat power spectrum for the curvature perturbation, which is switched on at K long, and then it switches off at K short. That is completely our assumption, and where those cutoffs are, it's completely up to us. And then so those set exactly these cutoffs. And the reason why at some point we wanted to put a cutoff, in this region here was not to, of course, propagate too much into the right-hand side. We could have done it, to have prediction also for the Einstein telescope, of course, of the Cosmic Explorer. But what we wanted to do was to arrive at a LISA experiment. So what defines the cutoffs is precisely the input by end that for the curvature perturbation. Okay, because the curvature perturbation is the source of the gravitational wave. So if you put a cutoff for the curvature perturbation, automatically there will be a cutoff in the gravitational wave signal.
Thank you very much.
Okay.
All right, so maybe one more very short question.
Sure.
Okay, now, so I have a question. So if you talk about, maybe a very naive question, so if you talk about supermassive black holes, and if they are not of astrophysical origin, then there must be also some kind of primordial origin. So are they classified as primordial black holes, and aren't they a smoking gun of primordial black holes?
I would say with some the answer is yes. In fact, you can form supermassive black holes coming from even tiny, much lighter black holes. So either by accretion. Unfortunately, there are strong bounds in this region. So, you know, when you span 10 to the 4, 10 to the 5 solar masses, you have strong bounds from CMB distortion, for instance. So its scenario is a little bit constrained. You can also form a supermassive object in a very nice way. In fact, suppose that what I was telling you at the beginning is wrong, is meaning that the primordial black holes at the beginning, they are not Poisson distributed, but they are strongly correlated. Okay, so strongly that when they are created, they are so gravitational way attracted that they form a bigger object. Okay, so that's a very nice, simple way to create a supermassive ones. So the answer is yes. You can form supermassive black holes in this way. The real problem is that accretion. I don't know of any robust and solid computation of accretion for masses larger than 10 to the 4 solar masses. So that's kind of so. I would say that it's possible, modulo this ignorance and this kind of difficulty of treating the physics, which is quite highly nonlinear, of accretion when masses are larger than 10 to the 4 solar masses. But I would say yes, it's. I mean, people have studied this possibility in detail, and now to say that it's a smoking gun, yes, I would say it might come from there, yes, but. If I say it's a smoking gun, I have doubts, because technically speaking, it's difficult to study the evolution of these objects up to very large masses. Unfortunately.
Well, okay, then I think we should stop here, and thank Antonio again for this very nice talk.
Thanks to you for hosting me. It was a pleasure.
Yeah. And so this was the last seminar this year. So enjoy your Christmas break, and see you next year. So goodbye, everyone.
Have a nice break yourself. Bye. Thanks.
Thanks. Bye.
Bye-bye.